Stress strain, part 3. Okay, now we're finally to the testing part. This is the fun part. Any time that you weld an aluminum or a steel or tie or whatever you weld, what you started with usually had been refined. The grain was pretty uniform, everything's very consistent. It's been said that the worst thing that you can do to any material, steel, aluminum, tie, is welding. Because when you weld it, that material, of course, goes to a liquid state, and normally it cools pretty rapidly. And one of the things that happens with any kind of crystalline group is the more rapid the cooling, typically the larger the grain size. Now there are other considerations, but that's a broad consideration. Well, larger grain sizes make your metal that otherwise is isotropic, meaning it has strength in all directions. It makes it not necessarily less isotropic, but it makes it a little bit more like really grainy wood. It makes it to where there are areas where failures can happen easier because the grain size is not small any longer. Smaller grain means that everything gets distributed evenly. So I guess a great illustration of this would be if you're going to get shot, I don't know anybody who wants to be a cop now, but if you were going to get shot, would you rather have a Kevlar vest that had really ultra-fine Kevlar and a lot of layers, or would you rather have a couple of layers that were really coarse? I would rather have the fine one, so that as it catches that first thing and then disperses that stress over a finer amount, it's going to keep me safe. The one that's bigger, it's more likely it's going to go right through it. It's going to find some kind of a location that can move through. And that's the same thing with grain size in steels. As the grain size gets bigger, when you have an impact, it gives it a place to move through. So this funny looking drawing or illustration that says inductor center is talking a little bit about what actually happens when you weld, in this case, steel. What you see is it says inductor center, that's where the flame was. And as you move away from that after the joint is finished, you see that it got harder, that's that up part of that curve, and then it got softer. And then it returned to its original strength that the manufacturer gave it to you in. So all materials do this. They don't remain the same after you weld them. So as a manufacturer, there's a couple of things you have to do. You have to think about the fact that people are going to weld this stuff. So you want to make sure that you have adequate thickness to make up for this place where it gets softer. And you also want to try to use alloys that are a little bit less sensitive to heat. And the other material shows a much smaller, the one that's called Cyclex in this particular drawing, is showing that its peak was a little bit lower than the other one, and its drop-off was a lot lower. So it was a safer material. It was more benign with respect to welding. Well, we had a lot of questions about this kind of stuff, and manufacturers weren't talking. So we were working with Columbus at the time, and we had a material that they were doing that we thought was pretty good, but from a marketing standpoint, we were getting killed by another manufacturer. They were doing a much better job than we were in terms of sales. And we didn't know if Columbus was doing a good job or a bad job, frankly. We didn't know. So we commissioned a test at Lehigh University, and we said, we really want to know what's happening when you weld these things. Are they stronger or are they not? So we commissioned a test. We had the top 4 makers of tubing. We had True Temper, Dedichai, Columbus, who else? Reynolds, yeah, we had all 4. The big 4, and then we did a controlled sample with Tongate Prestige just to set the calibration machine up. And this was done by a professor, his name was Dr. Terry Delph at Lehigh. So we took tubes that had all the same wall thicknesses, same diameters, and we cut them off so that we had a 32 thousandths wall, a 0.8 millimeter wall. They were all cross-mitered at 90 degrees and welded up by the same guys. We just marked them 1, 2, 3, 4, so nobody knew what they were. So, blind test. Had Jeremy at CSIP weld him up. He's a great welder. He's done a lot of stuff like this. So we took those T-samples, we shipped them off to Lehigh. And the guys there were really smart. They figured out a way to test these such that you took a lot of the experimental error out, which is obviously what you want to do if you're going to test something. They figured out a way to machine a piece that would hold, well, I'll just draw something. Basically, we had a head tube, and we had the piece that was the sample that was welded 90 degrees like that. And then they made a special machined yoke that would take a hold of this and then pull it from this side. And they made an internal and an external grip to hold the tube from this side and pull it. And then they had, what we had them do is put strain gauges that would give data at the bottom of the miter, at the edge of the miter, and back in the heat affected zone where it was the softest. Because we thought, you know, for sure, these things are going to fail where they're the softest. It's the area where this yield point is going to be the lowest. Well, to our shock, it didn't happen that way. The first thing that we did was we calibrated with the Tonge Prestige materials, and I didn't bring experimental data, but I'll make that available on the class periods. We pulled them apart, slowly, and these were at the top of the range of what this tester would do, so the resolution of the test was really, really good. And I'm not an expert in strain gauge data, so I had to have Dr. Delft tell me, well, what does this mean? And we saw, visually, we saw some of these parts that had like a stretch and tear failure. And we had others that just had a nice clean break, almost like a Coke bottle. And we were sort of mystified as to what happened. Well, look at this is, I guess it's page 7, assumptions about what would happen in the heat affected zones. When you weld this stuff, of course, things do happen. We thought initially that this spot, the heat affected zone where it's really soft, is where they would fail. We also thought that the materials with the highest numbers from the manufacturers would be the ones that would win the day. Well, it didn't work out that way. What actually happened was materials that had a very specific amount of ductility were the ones that went the furthest. They went 22% further than the ones that had the highest tensile numbers, which was a shock for us. We had no idea that this would turn out this way. So what were the actual test results? The material with the highest ductility, measured as 12 to 13%, took 22% more load. It's a lot. It's not a little bit, it's a lot. We looked at the strain gauge data, and I did not know what this stuff meant. I'm not an expert in strain data. But here's what was going on, and this is fascinating. Here's your weld sample. Here's your weld. And around that weld, there are little pinpoint stresses. And this is what the strain gauge data told us that we would have never figured out. The materials that were ductile would have a pinpoint stress. They would actually go through a little cold work cycle, just like this, and they would harden. They would harden enough to stop what was coming at them. So they would actually stabilize. Then the next pinpoint stress would emerge, the next place that was weak. It would do the same thing. It would actually cold work at a micro level. It wasn't anything that you would ever see. And then it would push back. And this happened hundreds of times with the materials that had the right kind of ductility. So what ended up happening is, because it was able to share that pinpoint stress load that otherwise would have been the first place that it would have started failure and it would just pop. Instead, it ductily cold worked, it got stronger, it pushed back, it had the next same thing. The next soldier did his pushback, and it went over and over and over. That was the secret to making great tubing, is you need something that has a specific amount of ductility to push back, and there are some magic numbers that we discovered. And this is material that none of the manufacturers are talking about. They may know it, but they haven't published it, and I've talked to them and they act like they don't know. don't know what the real answer is. What we discovered was that if you had a material that was really, really hard, wherever that first pinpoint stress was, it would hold. It would try to continue to hold, 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 more and more load, and bam, it would break. So we discovered some things that we really did not expect. None of the materials failed in the heat effect zone, which was a shock. We thought, weakest spot, it's got to fail there. Well, the reason it didn't is all of those pinpoint stresses were here. By the time it got to here, the load was radially shared around that tube. And it really wasn't changed that much to begin with. I mean, it was annealed, yes, but there wasn't a pinpoint stress that the material was having to hold against. It was being radially shared. So it was kind of an interesting phenomenon. We didn't expect that at all. One of the things I did want to say, because there might be some statistical guys here, is we only did 3 samples, which is a tiny amount. Normally, if you're going to publish, which we weren't interested in publishing, you need 25 samples of something to be statistically significant. But having said that, 3 of the 4 samples we did had a standard of deviation equal to 0.1%. They were really tight. I mean, it was basically like if you can shoot a precision bullet and you can shoot it 3 bullets and they all go through the same hole. It's pretty much what this was saying. There was one that didn't do as well. It turns out it was true temper, and what it seemed to suggest is that their material was excellent, but their ability to control their hardness was not as good. So it just said that quality control and process do matter. So what are the conclusions? Well, there's one of them. Tensile and hardness matters. You need this to resist, but at some point it is going to fail. And when it does fail, you want this to be able to stretch it out. And if a manufacturer does their job right, they figure out how to work the best number here with a certain number here, which happens to be 12 or 13%. The distance from here to failure is a number, and it's called elongation. As it turns out, for bicycle tubes, because they're thin, they have a cross-section, and they have a lot of stress right around where they're joined. You need about 12 or 13% of this. You would think, well, don't you want more down here? No, because that means the material is lower on the scale. You push it up to the point where it's about like this, and then you get your percentage, and then as you measure the area can be 2.5 times, in some cases, what the highest possible would be. So that's what you want so that these things don't fail. Okay, ductility and elongation matters. That's part 2. There's just a need for the manufacturers to really do their homework, and frankly, most of them do. They do a pretty good job. And then from there on in, what you can say about this, and this is just from what we know from these experiments, is that if you can get 12 or 13%, that's kind of the holy grail number, whether it's steel or aluminum or even titanium. That means that you will have pushed this yield point as far up the scale as you can while still failing gracefully. So that's like the optimum number, whether it's 4130 or an air hardening steel or 325 tie. It doesn't matter. It has more to do in this case with the geometry, with the fact that you're dealing with thin wall tubes that take a stress. So that concludes this part of things. Are there any questions? Crickets.